In the last video, we talked about orthogonal bases. We're going to start to look at why they're important, and we'll prove in this video Theorem 4.2.2. Let V be an inner product space. Let B be an orthogonal basis for V. For any U in V, if I want to write U in terms of the bases, all I have to do is to take U dot V1 and to divide it by V1, V1. U V2, 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 and U Vn, Vn, Vn. So again, this is a case where writing as a linear combination doesn't have anything to do with the inner product, but if we take a basis that's nice for this inner product, then finding the coefficient can be done using the inner products themselves. All right, so let's prove this. It's going to look a lot like the last proposition we proved, so I'm going to use something that we used there. So you assume that it's C1 V1 plus Cn Vn. All right, so I'm going to dot it with Vi. Actually, let me put it on the other side. I mean, it didn't matter for the last one, but the way I wrote it above, this is going to be better. So on the left, I'm going to get U Vi. And on the right, if you remember this argument here, on the right, if I have a linear combination, most of them will go to 0 because they're orthogonal, and I'm just going to end up with the ith term. So this is going to give me Ci, Vi, Vi. And so Ci will be UVi over Vi, Vi. And notice that this isn't 0 again. And so I can divide by it. Okay, that's it. All right, super simple, super nice. And it actually gives us a corollary for any orthogonal basis. If you want to know what the coordinate vector for an element U is, all you have to do is take a bunch of dot products. All right, so it's going to be UV1 over V1V1, and then UV2, V2V2, UVN, VNVN. All right, there's a bit of notation clash here. There are dot products, inner products, and here that's a vector. So I'll try, I mean, it was hard here, but I'll try to use vertical vectors in this section just because otherwise it's a bit of a mess. All right, for you, this vector, consider V with the dot product as inner product. I'm going to take this basis. I'm telling you it's an orthogonal basis, so you don't have to check. I have this vector here. I want to find the coordinate vector, so I'm going to use this. So I need to find U dot, let's call it V1. All right, so that's 2 times 1 plus 0 times 1 plus 3 times 2. I get 6, 7, 8. And I need V1 dot V1. So that's going to be 1 squared plus 1 squared plus 2 squared. That's 2 plus 4, that's 6. So the first coefficient, first coordinate will be 8 over 6. All right, second one, U dot V2. I'm going to get, so this one is V2, so I'm going to get 2 plus 0 plus 0. I get 2 V2 V2, that's 1 squared plus minus 1 squared, that's 2, so I get 2 on 2. V3, sorry, UV3, that's going to be minus 2, 0 plus 3, that's going to be 1, and V3, V3, that's going to be, this one's V3, so it's going to be 1 plus 1 plus 1, it's going to be 3, so last one is a third. And you can even check, right? You can check this. If I take, so that's 4/3, 1 1/3. If I take 4/3 times V1 plus V2 plus 1/3 times V3, you should be getting 203. Right, so if you want to test your answer here, you can definitely check that it's right by just re-putting the coefficient, the coordinates in the linear composition.